Exponential functions. So we've been looking at expressions upon expressions upon expressions and manipulating them and simplifying them as best we can to come up with something that's easier to look at or potentially just in a different form. Sometimes it doesn't always seem like it's that much easier to look at. Well, the functions as a whole, though, are what we need to be observing next. And now we need to remember that being exponential, it's all about repeated multiplication. So exponential functions are going to be functions where the dominant operation is repeated multiplication. Things that causes to happen are we get a non-constant change. It's not like linear functions where we had our slope that was the same every time. We added 1 to the x and we would always get that same change in y, which is going to generate a curve rather than a line. Generic form of these functions is going to be y equals a times b to the x. That x, our independent variable, is actually the exponent rather than being in line with everything else. So if it's anything of the form y equals a times b to the x, we need to specify a little clearer that a can't be 0 and b has to be positive. The base of that exponential is always going to be a positive number. And a can't be 0 because if a were 0, it would wipe out the entire right side and we just get y equals 0, which is actually a constant function, not exponential. So some examples of these. We've got 4 different looks to the graphs. We have graphs that seem to increase, we have graphs that seem to decrease. What we can notice is that the change there was that I had either a positive a value or a negative a value. And then I've got graphs that are decreasing to almost nothing and increasing from negative to still negative, but getting closer and closer to 0. Again, the only change from red to blue in the graph on the right is a positive or negative a value. So linear functions, I mentioned before, it was all about slope, right? We had a constant change as we went term to term. Now, another way to talk about that would be that we had a common difference. Things are a little different when we deal with our exponential functions. Instead of having a common difference, we're dealing with multiplication. Difference is indicating that we could subtract values and end up with the same thing every time. -1 minus 1 would have been -2. 1 minus 3 would be -2. 3 minus 5 would be -2 as we work from the right to the left across that table. Well, it's slightly different here. We've got the dominant operation is that our y values are being multiplied by 3. So we've got a common ratio. Now the reason it says it's a ratio is because if I compare output values, those y values, 27 divided by 9 would give me 3. 9 divided by 3 would give me 3. 3 divided by 1 would give me 3. That turns out to be the number that was multiplied each time we added 1 to x. So some actual scenarios where exponential functions are going to be something we make use of. This is actually where it makes more sense to real life. Population growth. Population growth is exponential. You don't just add one person every so often. Populations multiply. Could be peoples, could be animals, could be bacteria. All of those things. Based on the quantity you have, you gain more each and every time that you calculate. So investments. We all want to know how our money works and how things work when we put it in banks. Well, interest, whether it be for us or against us, is all based on an exponential model. And half-lives. We might have talked about these in a science course before, but the idea that over a certain period of time, the quantity of something that you have diminishes by half. Well, that means that every so often you multiply by half of what you had, and that's the new value for that quantity. Carbon dating is a popular one. The half-life of carbon-14 is something that's very interesting to people because it can determine the age of bones and how long ago someone lived when they dig up something they're not sure about. So we're going to need to graph these. Y equals ab to the x. We need to know what its parent function looks like. And there's 3 important values on that parent curve. We've got the point 0a, which would be our starting point when we really want to think about these curves. The point 0a represents our y-intercept. The point 1, ab, and the point -1, a over b. And then we just draw a smooth curve through those 3 points. Well, where do those points come from? If we made a table, still not using any numbers in our function, but if we made a table, when x is -1, that function would read a times b to the -1st, which we know b to the -1st is really 1 over b. So a times 1 over b gives us the value a over b. 0. When x is 0, a times b to the 0 is really just a times 1 because everything to the 0 power is 1. It's where our point 0a comes from. And a times b to the first, well, b to the first is just b, so it's really a times b. Those are the 3 points that become important to us. There's this other phenomenon that occurs with these functions, though. We have what we call a horizontal asymptote. In this case, specific to this graph, that horizontal asymptote is the x-axis. It's a value that our curve approaches, but never really gets there. If you think about it, no matter how small a number you raise b to, small being farther left on our number line, seriously negative numbers, you'll never really get 0. If you're still multiplying that number by something, you'll always have a quantity remaining. That causes the graph to appear the way it does. The curve appears to level off, but in all actuality, the space between this curve and the x-axis is getting tinier and tinier and tinier until you really can't identify that it's there at all. So here's one to actually try. Let's graph y equals 2 times 3 to the x. Now would be a good time to pause. We plot the point 0a, which in this case is 0, 2. We plot the point 1ab, which is 1, 3 times 2, or 6. And we plot the value negative 1 a over b, so negative 1 2/3. Then we just draw a smooth curve between the two, making sure that we don't touch the x-axis. We want to represent that that asymptote actually exists. Now, other things we can determine. What's the domain of this function? Well, as we look left and right, the function appears to continue left forever, and even though it's going to be well away from the x-axis because it's going to increase infinitely, it is going to continue to move to the right. So our domain would be from negative infinity to infinity. Being careful to use the parentheses and not the brackets because we don't include negative infinity and infinity in the domain. And then our range. Well, if the asymptote defines a value that we'll never achieve, then really our curve bottoms out before it gets to 0 along the y-axis. If that's the case, then our range would be from 0 to infinity because it never gets to 0 and it continues upwards forever. Those negative y values don't really exist for this particular curve. You can make a few more examples up on your own if you really choose to. See what you can do to manipulate it around, and checking Desmos to see if your answer is correct is never a bad idea.